Okay. Okay, let us continue. I will take the question in the chat after we finish our derivation. So now we looked at how to compute dou E by dou Wij2, right? Now similarly, I can compute dou E by dou Wij1. Okay, so this is from input unit I to hidden unit J. Is that clear? So how do I do that? So let's say this is my OI, and this is my weight Wij of 1, which is going to some OJ of 1, and the derivation is OJ of 1 multiplied by 1 minus OJ of 1. Okay. Now from this hidden unit, we know that there is going to be a bunch of units, like bunch of weights, m weights going to the output units, right? Like so, you have Wj1 of 2, Wj2 of 2, up to Wjm of 2. They all go to the output unit. We have already computed the error up to the output unit in the previous step. So let's just call it as del 1 of 2, del 2 of 2, and del m of 2. Is that clear? So now this is actually simple. Like so, if I want to compute gradient with respect to Wij of 1, I will take all these dels, multiply by W. Okay, I sum them together, and then multiply by this. So that will be my del for updating Wij, right? So it's simple, like so. The back propagated error up to this part is given by summation over Q is equal to 1 to M Wjq of 2 del Q of 2, which is integrating all the dels and then multiplying it with Oj of 1, 1 minus Oj of 1. Is that clear? So we're going to call this whole thing as del J of 1. Now, dou E by dou Wij of 1 is given by del J of 1 multiplied by OI. Is that clear? So once you have these gradients, then you can do your gradient descent, right? So far we discussed only for computing gradient with respect to one example. Now you can actually generalize this. You can compute gradient with respect to, let's say, 10 examples, right? Like, or all the examples, right? Like, depending on what you are using, like you're going to use different versions of gradient descent. Like if you use all examples to compute the gradient, you're going to use the full batch gradient descent, right? If you use only one example, then you're using the stochastic gradient descent, right? And if you use, let's say, some k examples, then you're using mini batch gradient descent. Okay, so next week we will talk about like improvements to gradient descent and like better optimization methods in general. Okay, but for now, like these are simple things that we can do. Is that clear? Any questions so far? Okay, I forgot to charge my laptop. Okay, 1 second. Okay. Any questions? Okay, so now when you have more than one example, okay, or in other words, like when you have a mini batch of examples that you want to compute gradient together, you can actually do it much more efficiently by writing the same backprop algorithm, but in matrix form. Okay, now how do we do that? So consider a matrix D2 which has the derivatives of the output unit, okay, as in the diagonal. Okay, so you have O12 multiplied by 1 minus O12, okay, O22 multiplied by 1 minus O22, and so on. OM2 multiplied by 1 minus OM2. The rest are all 0. Okay, this is a diagonal matrix for the derivatives of the output layer. Similarly, you can have D1, which is the derivative of the input layer. It has O11, 1 minus O11, and so on. Okay, and I can also have derivative of the error function as a vector E, which is O12 minus T1, O22 minus T2, and so on. Okay, once I have these vectors and matrices, I can write my complete gradient update rule in a matrix form. Okay, so my del2, the backpropagated error for computing the weight, second layer weight gradients, is nothing but D2 multiplied by E. Simple, right? So then my del1 is given by D1 W2 del2. Is that clear? So now I can actually write my gradient update rules just by using vector, vector, matrix, vector, and vector matrix operations. Okay. Now these kind of vector matrix operations can be done efficiently in GPUs. Okay. So which is one of the reasons why neural networks are extremely popular now. Like, so you can use GPUs and train your neural networks faster, okay, instead of just using CPUs. Now, I know a lot of you, or almost all of you, are using Colab for your assignments, right? Like, so, like, you can actually ask for free GPUs in Colab. Like, so instead of having a CPU, you can ask for a GPU so that you can train your neural networks faster. So I think some of you are already trying neural networks for your Kaggle competition. For others, like after today's lecture, I think you will have the necessary background to try it. Like, so if you're trying neural networks for your Kaggle competition, like, so you can make use of the GPUs that you get in Colab. Is that clear? Any questions about neural networks? Now, there is a question in the chat. So how the neural hidden layer architecture can impact the result? Okay, well, of course, like, so now from simple models, like we are going more towards more and more complex models, right? Like, so now it is not very clear how many hidden units to use or how many hidden layers to use, right? Like, so now this is all hyperparameter now. Now you're going to have hundreds of hyperparameter now. Like, so, like, it is getting more of an art to come up with these things, like, than having a more principled way. Okay, so like, for example, like, well, we are going to talk about more layers now. For example, there is no rule of thumb on how many hidden units you should have. So can someone tell me, okay, let's say I want you to train a one hidden layer neural network. Okay, so you have the input and then the hidden layer and then the output, right? Now, one good thing here is input is fixed. We cannot change it. It is given to us. Output is also fixed. We cannot change it. It's given to us, right? Like, so similarly, the output activation function is kind of fixed, right? Like, so because if you have a real value, you cannot put sigmoid or tanh. If you want a probability output, you have to put sigmoid or softmax, right? So there is not a lot of room like for flexibility in input and output units. However, there is a lot of room for flexibility for the hidden layer. Now, can someone tell me some heuristics? So how would you, let's say I ask you to train such a network. So how would you pick an activation function, or how would you pick the number of units in the hidden layer? Yeah.
Normal validation training.
validation training. Okay, so how would you do that?
You split the data set and
Oh, no, I'm not talking about how to do validation, but let's say I want you to decide the number of units. Okay, so let's say the input is 500 units, output is 10 units. Now, how would you pick a range for hidden units? So what will be your strategy?
just like common sense, try some values increases the performance and keep increasing the number of a decrease in performance maybe.
Okay, so you will, let's say you try 100 units, 300 units, 500 units, and 1,000 units. And you see that when you have 1,000 units, it's not working so well. So probably you should reduce, right? Like you will do a little bit of back and forth in figuring out the number of units. Okay, now this is very normal. The moment you go to deeper networks, let's say I have 5 hidden layers instead of 1 hidden layer, you cannot do this anymore, right? Like, so you cannot try every possible number of units for every layer, and then you do this combinatorial multiplication of choices, right? Like, so then your options are limited. So probably you would try 5 layers of 100 units, then 5 layers of 200 maybe, like so. So you were given a computational budget. So here is one thing that I want you guys to think about and also learn, okay? So, which was also the purpose of the third assignment. Like, so doing hyperparameter tuning is one of the trickiest thing in machine learning. You might know the theory, you might know how the algorithm works, but making it work is a totally different story. Okay, so it requires a lot of experience in tuning these hyperparameters. Like, so I think towards the end of the lecture, the last week, we will talk about tips and tricks to do machine learning, like so where we will talk in detail about like how to tune your hyperparameters, like how to set up your experiments and so on. But for now, the general thing to remember here is like neural networks brings you way more hyperparameters. So you cannot do blind hyperparameter search. Is that clear? Okay, I think that concludes our discussion on basic neural networks. Okay, now very quickly, we are going to talk about like how to go beyond simple one-layer neural network and train like many layer neural networks. Okay, now this is not a course on deep learning, so I try to reduce the deep learning content as much as possible. Even then, we had this huge lecture on backdrop, as you can see. But to learn more about what we are discussing today, I highly encourage you to take the deep learning course by Aaron Colville next semester. As I mentioned before, like it's one of the famous courses in Montreal, and it gets filled very quickly. So probably it's too late, but it's a course that I highly recommend. Okay, so what is a deep neural network, right? Like, so any neural network that has more than one hidden layer, we can call it as a deep neural network, just as a rule of thumb. Okay, now one way to think about deep neural networks is it is just a sequence of nonlinear functions, right? Like, so you take the input x, you pass it through some nonlinearity, you get h1, and then you get h2, and then you get h3, let's say. Finally, you have the y, and when you're doing backprop, you will also put the error as another layer, so you have some error. Is that clear? Now, if you remember our discussion on universal function approximation theorem, it's just last week. So can somebody tell me what does universal function approximation theorem say? Yeah. Anyone? So how about people in the end of the room? They're all busy with their laptops. Anyone? So what was universal function approximation saying? Okay, there are answers in chat. So what about the class?
can approximate any function with a sufficiently large hidden layer?
Yeah, so you can approximate any function, like continuous function, arbitrarily well with a single hidden layer neural network, given you have enough number of units, right? Like, and we also discussed how this enough number of units, like, is the bottleneck, because the number of units required is going to grow exponentially, right? At that time, I did mention that there is a way around it. So the way around is, instead of having one hidden layer which has exponential number of units, you can get the power of such neural networks by having a sequence of nonlinear operations, right? Like, so that is the idea behind having very deep neural networks. Okay. Now, however, like, well, I have a logical argument, right? Like, so however, in practice, if you take the backpropagation algorithm that we discussed, okay, and try to train 5-layer sigmoid network, a 5-layer network with sigmoid activation functions, okay, it will not learn anything. The performance is going to be bad. Okay, forget about 10-layer or 100-layer. So just for 5 layers, the performance is going to be bad. Okay, so why is that the case? It was not very clear in the beginning. When I say beginning, in 90s. Okay, so in 90s, when people were trying to use more than 1 or 2 layers of neural networks, they saw that it was not learning properly. Like, the performance was not better than a 1-layer network, so they would just not do more layers. Okay, so however, in 90s and like early 2000s, like, so there was a lot of research on why this is the case. Okay, and one of the main reasons that researchers found, like, why this is the case, is the problem of vanishing gradients. Okay, so now what is vanishing gradient? So far, we have seen 2 types of activation functions, right? Like, for hidden layers, like either sigmoid or tanh, right? Now, let's think about the range of these activation functions. Now, let's take sigmoid first. So what is the range of sigmoid? 0 to 1. Okay, what is the range of tanh? Minus 1 to 1. Right? Now, when you differentiate these functions, okay, sigmoid and tanh, their ranges are going to shrink further. Okay, so sigmoid dash is going to be between 0 to 0.25. This is sigma dash. Okay, now tanh dash is going to be from 0 to 1. Is it clear? Now, we know that when we do the backprop, in every unit, we are multiplying the incoming gradient with the sigma dash or tanh dash, right? So essentially what happens is, as my chain gets longer, for a lot more times, I'm multiplying my incoming gradient with something which is less than 1, right? It's actually bad with sigmoid. With sigmoid, every extra node in the backprop, I'm dividing my gradient by 1/4 in best case. Okay, so now you can see that with just 5, you take a gradient, you divide by 4 5 times, you'll get a value very close to 0. Okay, so which means, let's see that through the picture. So this is my x. I pass it through W1 to get H1. I pass it through W2 to get H2. Okay, I pass it through W3 to get, let's say, Y, for example, and then there is error. Okay, now let's talk about dou E by dou W1. So W1 is all the way here, right? So my differentiation is going to be dou E by dou Y, first step. Then I do dou Y by dou H2, then dou H2 by dou H1, dou H1 by dou W1. Is that clear? Now you look at this particular entry, dou H2 by dou H1. Okay, this is nothing but dou by dou H1 of, let's say, sigmoid activation function, sigma of W2H2 plus bias. Okay, now this is going to be sigma dash multiplied by W2, right? So this particular entry has a sigma dash. Similarly, every entry is going to have one sigma dash, like for every layer. Okay, so in every, as you go more and more deeper, like for every layer extra deep that you're going, you are actually multiplying by 1/4, like if it is sigma. And this only gets worse when you have more layers. Like, so for example, let's say we have 5 layers, then dou E by dou W1 is given by dou E by dou Y by dou H5, okay, then dou H5 by dou H4, dou H4 by dou H3, dou H3 by dou H2, dou H2 by dou H1, dou H1 by dou W1, right? Now, these 4 terms that you have here, all of them are going to have a value between 0 to 0.25. So you take the gradient, you go through this chain, your gradient is already gone. Is it clear? Your gradient vanished, like when you try to go 5 layers deep. Okay. Now, how do we solve this problem? Any ideas? Yes.
Using a linear activation function, like a ReLU.
Okay. So we have to change the activation function. Well, by the way, this is from 2006. So in the last 15 years, there are numerous solutions to solve this problem. So, and I would appreciate if somebody who has not gone through this solution to come up with a new solution on the spot. There are a few answers in the chat. Yeah.
You could scale the gradient based on how deep the backdrop is.
That's a good solution, which is also not in the notes. Okay, so I appreciate it. Yeah, so like the solution is you can just scale the gradients as you go down so that they don't vanish anymore. Okay, that's actually that is a good solution when you have a feed-forward architecture. Okay, so we will not talk about recurrent architectures in this course, but this solution works perfectly fine for feed-forward architecture. Any other solutions? Okay, there are a bunch of solutions in the chat. So I think other activation functions, smoothing, dropout. Okay, so in general, we know what's the problem, right? Like, so the problem is the activation function itself. Like, so when you use sigmoid.nh, it shrinks things. Now, either you deal with the shrinking, which is what his solution is, like you just rescale it, or you just completely avoid the shrinking by using something like other activation function. Okay. Now, as I mentioned, there are like many solutions in the literature, but okay. So there are many solutions in the literature, but just for this lecture, I picked 3 different solutions, which would give you a sense of diversity in solutions. Okay. So the first solution we are going to see. Okay, somebody's mic is on. The first solution that we are going to see, which was also the first solution for this problem, which started the whole field of deep learning, is the idea of greedy layer-wise training. Okay, so this was a solution by Jeff Hinton in 2006, which is now a seminal paper in machine learning, like which introduced this neat trick that we are going to see today. But the thing to remember or thing to note here is their trick doesn't solve the problem. Okay, it just bypasses it. Okay, we are going to see that why. Now, before we understand greedy layer-wise chain, okay, so we are going to talk about another type of neural network, okay, so which is the idea of autoencoders. Okay, now what is an autoencoder? An autoencoder is a neural network whose output is same as its input. Okay, so that's why it's called autoencoder. Okay, so you take input X, you pass it through some hidden layer, okay, and then you get the say here's some output Y, and we are going to set Y is equal to X. Is that clear? Now, in terms of equation, H is given by f of X, for example, sigma of Wx plus B, okay, and Y is given by G of H. One example is just BH plus C. Okay. Now we are going to train this autoencoder by using reconstruction laws. The goal is to reconstruct the input X as accurate as possible. Is that clear? Now, my first question, why would I do something like this? Like, why do I take the input and pass it through a projection and then try to get the input back? Any idea? Yeah.
If we have some point to the middle layer that has less units than the inputs, we could use only the first part of the network. It's compressing.
Okay. Yeah. So one application, as you suggest, is compression, data compression, right? Like, so if you want to compress your representation, you can take, let's say, 100 unit input vector and have a hidden vector which is only 20 units, let's say, okay, and try to project this 20 back to 100. Now, if my reconstruction loss goes to 0, what does that mean here? It means that I have found a perfect compression of these 100 units to 20 units so that I can actually decompress it back if I want, right? So I'm keeping all the knowledge, but in 20 units instead of 100 units. Is that clear? Now that is the idea. That is one use case for autoencoder. Like, so you can encode things into this low dimensional space, okay, so that you can do compression. Okay. Now, why should we do compression? There are a lot of applications for compression. Okay. So first of all, simply storing these things. Like if you want to store in low dimensional space, you can compress. And in the beginning, when we talked about overfitting, we also talked about how we should remove some features if there are too many features, right? So now compression is one way to get better representation for yet another class. You can do this autoencoder, find this 20-dimensional vector, and use that 20-dimensional vector as input to any classifier, right? So you can do a lot of things with this compressed unit. Okay. Now, I think probably next week. So we will talk about like other dimensionality reduction approaches like principal component analysis and so on. Like, so then we will come back to autoencoder to see the connection between dimensionality reduction, classical dimensionality reduction methods and autoencoder. Okay. But for now, like we know what is an autoencoder, like we know the purpose, and the loss for this autoencoder is going to be reconstruction error. Okay. In the case of real valued input, it's simply x minus g of f of x, the whole square by 2. This is the usual least square ROS, like if you have real valued input, okay. But if you have binary x, then you can use the cross entropy function. So which is summation I is equal to 1 to p minus xi log yi minus 1 minus xi log 1 minus yi. Is that clear? Now, typically, let's say this is my autoencoder, which takes x. This is my h. This is my y. H is equal to f of x, and y is equal to g of h. Right? Now we are going to call this part, okay, as the encoder, which encodes my input to low dimensional representation. Okay. Now similarly, we can call this part as the decoder. Is that clear? Now, an autoencoder is basically an encoder followed by a decoder, okay, so, which has the same output as the input. Okay. Now, can somebody guess what would happen if the number of units, hidden units, is more than the number of input features? Let's say I have 10 input features. My head size is 20. What could happen? So first of all, I'm not compressing. I'm doing the opposite of compressing. But what kind of solution do you expect? Okay, there are good answers in chat. Yeah.
The first X, if you have 10, the first 10 are going to be just straight line map, and then you have 10 others that do nothing.
Okay, yeah. So what could happen is, it need not be first 10. We don't know which 10, but what could happen is 10 of these units might do identity mapping, and the rest can do whatever they want. And this identity mapping will be taken to the output unit, right? Like, so nothing useful is learned. So, however, in practice, when you do mini batch gradient descent instead of full batch gradient descent, this doesn't happen often, but there is a chance for this to happen. Okay, so that is why people normally don't use autoencoder with more units in the hidden layer. It is normally more useful like when you have lesser units in the hidden layer, in which case it acts like a compression algorithm, or like a dimensionality reduction algorithm, or just a representation learning algorithm. Okay, it is just learning a representation. In this case, it happens to be a smaller representation or shorter representation for the data. Is that clear? Okay, now we can go back to our solution. I think we have the basic tool for greedy layer-wise pre-training. Okay, now here is the idea. I give you the input X. Okay, now you're in the first step, given the input X, I'm going to train an autoencoder. Okay, simple. So I take the X, I pass it to H1, let's say, and then I get the X back. We are going to call this as W1. Okay, now you can have a separate layer of weight here, or you can also have just W1 dash, or the transpose of W1. Okay, people often share the weights for encoder and decoder, like so, because if you think about it, encoder is taking 10 to 10, let's say 20D to 10D. Decoder is doing the opposite, right? Like 10D to 20D. So you can just use the transpose of the same weight in your autoencoder. Okay. Now you train this autoencoder. Okay. After you finish training this autoencoder, in the second step, you're going to throw the decoder and just keep the encoder. Is that clear? Now, I'm going to take all my data and project it up to H1. Okay, so this is my new representation. I'm going to train a new autoencoder on the top of H1. Okay, so treating H1 as input. Okay, I'm going to train a new autoencoder which has H2, and this is W2 dash, and the output is H1. Is that clear? So when I'm doing this, I'm going to freeze this part. Or in other words, when I compute gradients, I will not compute gradient with respect to W1. W1 is fixed. Okay, so the data comes here, and then I train this autoencoder. Is that clear? Now you see what I'm doing, right? Like so. Now after training, I can actually discard the decoder again, right? So I can discard the decoder, okay, and I can repeat this as many times as I want. Let's say I repeat it for k times. So then I have this layer X followed by H1, okay, followed by H2, okay, up to HK. Is that clear? Now the K is a hyperparameter. I can train as many layers as I want. So once I train K layers, I can actually take this network and add a classifier on top of it for my problem. Let's say my problem has a 10 class classification. Then I will add, let me change the color. So I will add an output layer Y with WK plus 1. Is that clear? Now I'm going to do my normal neural network training with this layered architecture. The big difference here is all these weights from W1 to WK, right? They are all initialized through this layer-wise training procedure. Okay, I call it greedy layer-wise training because in every layer I wanted to do the best I can for reconstruction. Okay, so I'm going to do this greedy layer-wise pre-training. Okay, and initialize these weights, and I will randomly initialize WK plus 1. Now I'm going to train all these parameters. Okay, now if you think about it, what this solution is trying to do is to come up with a good initialization for all these weights. Okay, instead of starting with random initialization for all these weights, in which case, okay, imagine you have random weights initialization and no gradient is coming, right? So what's the issue? The issue is you're getting really bad representation. Now, we know that we are not going to get gradients because of vanishing gradient. So we can very well start with a good initialization, okay, such that even if the gradients vanish, we have a good model to begin with. Okay, so with a little bit of fine tuning, like by doing this final step, we can get good performance. Is that clear? Is that clear? So the first few steps are known as greedy layer-wise pre-training. Okay, it's pre-training because that is not the classification task that you are interested in. Okay, it's just autoencoder. Final layer, like adding this final layer and training it end to end, is known as supervised fine tuning. Is it clear? Now, this is going to be better than plain back propagation. Okay, but has it really solved the problem? No, right? Nevertheless, this was a clever solution for that period because instead of solving the vanishing gradient problem, like we bypassed it, the gradients are still going to vanish, okay, because we are using sigmoid. Okay, however, the initialization is a smart initialization, so the performance is going to be better than, definitely better than training a 5-layer network without random initialization. Is that clear?